In this presentation, we will discuss the ChiSquare-goodness of fit test. The ChiSquare-goodness of fit test is useful for comparing qualitative variables. Up until now, our tests have been useful for testing quantitative variables, but now we get a test that will help us to test hypotheses about qualitative variables. Just a reminder, qualitative variables are not numbers. These are things like yes/no answers, colors, or voting preferences. Anything that is categorical is quantitative or qualitative variable. A few other terms that we will use are independent variable. An independent variable is manipulated by the researcher or precedes the other variable, and a dependent variable is what is being researched, what we want to predict. We'll be using these terms more as we talk about regression, but they're useful especially with the chi-squared test for independence. The goodness of fit test allows us to compare data from a survey or an experiment with some expected percentages. And so in this example, we have a market analyst wanting to see if candy customers have a particular preference among 5 possible flavors. And so he asks 100 people what flavor they would prefer, and the results are as follows. 32 prefer cherry, 28 strawberry, 16 orange, 14 lime, and 10 grape. Now, as always, we're really interested in whether or not this data reflects a true preference within the population, or if perhaps just by chance we happen to get people who like cherry and not so many people that like grape. The goodness of fit test allows us to test that hypothesis. So we want to know whether the sample data support the claim that customers in this population prefer some flavors over others. You see, it could be just by chance that we have this particular sample. Some terminology we'll use and notation is the observed frequency is f sub o, and the expected frequency I will use f sub e, the subscript there underneath the f. The chance or null hypothesis in this case is that all of the frequencies should be the same. Now in the future we might have, or on your homework, you'll have problems in which you're comparing a set of observed frequencies with a specific set of percentages. In that case, the null hypothesis or the chance hypothesis is that the frequencies would fit the percentages that are given. So it's just in this case we have this particular null hypothesis. Now, if indeed we expect all of the frequencies to be the same, then of the 100 people, we should expect 20 of them to prefer each of the flavors. Now, because of random chance, the expected and observed frequencies will almost always be different, and we want to know whether or not those differences are big enough to conclude that the population has a breakdown different than what is expected. So the steps of the chi-square test include the following. Parameters that we're interested in are the relative frequencies, in this case the relative frequencies of candy preferences. The null and alternative hypotheses are as follows. The null hypothesis is that the frequencies are all equal. I have an asterisk there to remind us that we might have to modify this for specific goodness of fit tests. For example, if we want to test whether or not a particular set of percentages matches the data, then the null hypothesis will be that the frequencies match the percentages. The alternative hypothesis is that the frequencies are not all equal, or in the case where you're given a set of percentages, it is that the frequencies do not match the percentages given. When using the chi-squared goodness of fit test, the distribution you'll be using is the chi-squared distribution. And it's important to note the degrees of freedom, which in this case will be the number of categories minus 1. So in the problem we've been working on, number of categories is 5 minus 1 makes 4 degrees of freedom. To get your chi-squared statistic, you basically just add up a bunch of numbers that you can compute very easily. The observed frequency minus the expected frequency squared divided by the expected frequency. Add those up, and you'll get the chi-squared statistic. And finally, the conclusion is basically the same as it has been with all of our hypothesis tests. If you're above your alpha level, which is usually going to be 0.05, then you reject the null hypothesis, or you accept the null hypothesis, and if the p-value is below the alpha level, you reject the null hypothesis. So going back to our example, the parameters of interest are the relative frequencies of excuse me, flavor preferences. The null hypothesis is that the population shows no preference for the candies. Each candy will appeal to 20% of the population. And the alternative hypothesis is that the population will show a preference for some candy flavor. Degrees of freedom, as I mentioned before, is 4, and so we're going to use the chi-squared distribution with 4 degrees of freedom. Now, to compute your chi-squared statistic, it's not difficult to do it by hand. You just make a table, and in the table we have the observed frequencies on the top, and the expected frequencies is next. Then I will compute the observed minus the expected frequencies, so in each case I subtract the 20 from the observed frequencies. So in the first case it's going to be 12. For the case of strawberry, 28 minus 20 is 8. And so on, all the way down to grape. Notice that some of those numbers are negative. That's fine. Next, we'll square each of these numbers. So you take 12 squared, you get 144. 8 squared is 64. And notice that with the negative numbers, when you square them, you do get positive numbers as your answers. Next, divide by the expected frequencies. It's very important that you are dividing by the expected frequencies, not the observed frequencies. So divide 144 by 20 and divide 64 by 20, and so on. And these are the numbers that I got when I divided each of those squares by the expected frequencies. Next, we're going to compute the chi-squared test statistic value, which is the sum of all of these. It's 7.2 plus 3.2 plus 0.8 plus 1.8 plus 5. All of that together makes 18. And then I compute the p-value. The probability is using my calculator, and here's what the screen looked like. I used the chi-squared CDF of 18, and then 1E99. That's the, of course, you know, it's the largest number our calculator can handle. And 4 degrees of freedom. You need to specify the degrees of freedom for chi-squared. And I got 0.001234, which is clearly less than 5% or 0.05. And so I'm going to reject the null hypothesis, and my conclusion is that there is enough evidence to say that population shows a preference for different candy flavors.